Okay, so these ones are just about graphing. So the first two questions on, the first three questions actually tomorrow, you have to graph. And then you have to answer some questions about the graphs that you get. So let's just go through the process and work on each one of these graphs and how you can tell what's what. So let's look at the first one. The first one will, because it's an odd power that's positive, it's going to look like a cubic. Now this one happens to be a cubic, but you might want to plug in things like -1, 0, and +1 are a good start for these types of problems. If you plug in -1, that would be -1 cubed, which is -1 times 2. If you plug in 0, you get 0. If you plug in +1, you get 2. And then my lines aren't quite as defined as yours, so on the quiz tomorrow, if your lines aren't very well defined, put them in there for me. And then at -1, we're down here at -2. At 0, we're at 0. And at 1, we're at 2. Now, it says at the top to describe the domain, the range, the intercepts, the end behavior, the continuity, the increasing and decreasing. So let's go through that whole entire process for this particular one. So we're doing number 1. The domain is all real numbers. We write that as -infinity to +infinity. The range is all real numbers from -infinity to +infinity. Both the x's and the y's have no issues. We can plug in positives, negatives, zeros, fractions, decimals, anything we want, okay? And then the range stretches from -infinity to +infinity, from low to high, remember when you're doing range. The only intercept, both the x and the y intercept, is that point right there, 0, 0. The left end's going to -infinity, the right end's going to +infinity. Please refer to notes we've done in the past as how to write it, or one of the note cards you might have created. As far as continuity, go back and look at your domain. Was there any issues for the domain? Remember, a discontinuity is where there's a jump, and infinite discontinuity like an asymptote, or where there is a hole. This graph has none of those. So it is continuous along that entire domain. Now most functions will be continuous along their domains. The ones that aren't might be a piecewise function. Sometimes will not be continuous on its domain. And then the last thing it asks is this function increasing, decreasing, constant? What is happening there? This is an increasing function. If we put our little math bug on there, he's going uphill. He's increasing as he walks from left to right. So we would say that the function is increasing from an x value of -infinity to an x value of +infinity. Remember, your intervals describe your x's. The word increasing, decreasing, or constant describes your y's. So there's problem number 1. Let's do number 2. You will notice that the power on this is a 4. That is a positive, even power. So it should look very similar to a quadratic. So it should look similar to a parabola. So again, it is not a bad idea to plug in -0 and +1. If we plug in -1, we get -2/3. If we plug in 0, we get 0. If we plug in +1, we also get -2/3. Remember, when you take a negative or a positive to an even power like this, it's going to make it positive. And so that's why that became a positive times -2/3 and stayed negative. So this should be a flipped upside down quadratic. So if we plug in some points here, that's about the most accuracy I need for these, that you give me a sense of what's happening. Now let's go through the process again as far as domain, range, and behavior, and all of the things that we need to know. The domain is all real numbers from -infinity to +infinity. There are no values that we cannot plug into this. We can plug in positives, negatives, anything we want. Now the range is a little different here. The lowest point is negative infinity, the highest point is 0. So the range goes from negative infinity to 0. It includes 0. That was something we were allowed to plug in, and we got out 0. So it is a y value that you would include in your range in a bracket. The only intercept is 0, 0. It is both an x-intercept and a y-intercept. So remember, intercepts are where you hit the x or y axis. As far as end behavior, both the left end and the right end go to negative infinity. Please write it the formal way. I just don't have a lot of room to do that. As far as continuity goes, once I start writing, I never have to quit. I can go from negative infinity to positive infinity. Now this function has a little bit of a change as far as its increasing, decreasing kind of stuff. If my math bug starts over here and starts walking to the right, until he gets to an x value of 0, he's going uphill, so it is increasing. So it is increasing from an x value of negative infinity to 0. Now increasing and decreasing uses that open bracket, because at that switchover point, it's not considered increasing or decreasing there. You'll explore that more in a calculus class. And then we are decreasing on the other side. Think he's going downhill once he hits an x value of 0, and once he goes any x value after 0. So from 0 to infinity, this function is decreasing. So there is problem number 2. Now problem number 3 explores our negative exponents. Negative exponents look like a reciprocal. Remember those two pieces, those two swoops. If it's a negative even, they're both going to be in the top, or they're both going to be in the bottom. If it's a negative odd, it's going to look like our standard, traditional reciprocal function that we learned in chapter 1. So this is a negative even with a positive exponent. So I hope you kind of get the idea that it should look something like that. That we should have two swoops in the first and in the second quadrant. Now if we go to do the same thing we did before and plug in -1, 0, and +1, -1 gives us a +3. 0 doesn't work. Like if you tried to enter that into a calculator, you would get an error. You're basically putting 3 over 0, which is undefined. And then we've got 3 times 1, which is 3. So you can see that both of our y values are up in a value of 3. So they're up high. So at -1, we're up at 3. At +1, we're up at 3. Now if you're not sure what else is happening, feel free to add more values into the list. You can even put a little asymptote here at 0 because you know that it is an undefined value. That is a horizontal asymptote. So now just go ahead, or I'm sorry, a vertical asymptote. And now just go ahead and make your swoops. They don't have to be super precise. I'm okay with that. But as long as you make sure that it doesn't touch the x or the y axis. As far as its domain, I was allowed to plug in anything but 0. To write that, we go from -infinity to 0. We skip across it and go from 0 to infinity. The range is all positive values, but we never hit 0. So the range goes from 0 to infinity. This one has no intercepts because it's never going to hit the x or the y axis, so there are no intercepts for this one. The ends are both heading to a height of 0, so if it asks for end behavior, for a reciprocal function, and as long as the reciprocal function hasn't been moved up or down, the ends will always go to 0. It is continuous along its domain because the only point of discontinuity is that 0, and the domain accounts for that. So it's continuous, just like its domain. They're essentially the same answer. Let's talk about increasing and decreasing for a moment. If our math bug is there, he's going uphill on the left portion of the graph. But if our little bug was on the right portion of the graph, he would be going downhill. So what that tells me is that it's increasing from an x value of negative infinity to 0, and it's decreasing from an x value of 0 to infinity. Now again, don't include the brackets there. And then let's do our last one here. So you'll notice that in the examples that I've done here, we had a positive even, a positive odd. We've had a negative even. Remember, the negative odd just splits it and it looks like your traditional reciprocal. So now let's explore the fraction ones. For the fraction ones, you want to first look at the denominator. If the denominator is even, it's only going to have one piece and it's going to look like a square root. If the denominator is odd, like this one, it's going to have two pieces. So it's going to kind of look like a square root with an extra piece on the other side. Now the number on the top determines what happens to the second piece. Okay? If the number on the top is odd, the second piece will be down in the third quadrant. If the number on the top is even, it's going to flip it up and make it positive. So if I were to guess, without plugging in anything, it's going to kind of look like when you made birds when you were a little kid. It's going to look like a little bird. Okay? So how do you check it? Well, again, all of these, a really good thing to do is to kind of think to yourself, okay, what happens when I plug in negative 1, 0, and positive 1? Well, when I plug in negative 1, the fifth root of that is negative 1. So that's nice. But when I square it, because remember, the bottom acts like a radical, so that's the fifth root. The top acts like a power, so that's like a square. And when I square a negative, what happens to it? When you square a negative, it becomes positive, right? So it's going to become a positive 1 times 4, which is 4. See how that's how we got that piece going up instead of down. If we plug in 0, the 0 to any power is still 0. Times 4 is 0. And then when we plug in 1, we get 4. Okay? So if you plug it in, we get 0 is at 0. At negative 1, we're at 4. And at positive 1, we're at 4. So what happens is it's just these square root pieces. There's like your traditional kind of looking square root. Yeah, it's a little higher than normal because of that 4. And then here is that piece on the other side. So if it's a fifth root, a third root, so if your fraction has an odd denominator, it's always going to have a second piece. It's just, where is that second piece located? If the top of your fraction is odd, it's going to go down here. If the top of your fraction is even, it's going to go up here. And you can use a calculator to figure that out. You could put, do the mathematical computation and see what happens. But that's what the graph looks like. Now that we've done that, let's go ahead and answer all the questions about it. The domain for this is all real numbers, so negative infinity to positive infinity. Remember, fifth roots work for everything. Square roots do not. So that's where you might have a change in your domain. Our range is from 0 to infinity, but 0 is a point that worked, so include that in a bracket. The intercept is that point 0, 0 again. That's the only point that hits the x or the y axis. These ends are going up to infinity, so you're looking here to determine your end behavior, so those ends are going to infinity. It's continuous along its domain. There's no holes, gaps, jumps, or breaks in the graph. So you can look at that for the continuity. Now let's talk about increasing or decreasing. So we got my little math bug. He's going for a walk. Initially, he's starting downhill. He goes downhill until he hits an x value of what? 0. Then, once he hits 0, he's going to start going uphill, right? So how do we write that? Well, you say that it's increasing from an x value of -infinity to 0. And I'm sorry, I flipped him around. He's going downhill. So it's decreasing from -infinity to 0. And then it's increasing from 0 to infinity. So that is your examples about graphing. So there'll be 3 examples, or 3 questions tomorrow about graphing. And they might ask you a variety of questions about the domain, the range, the intercepts, and all of those things. So make sure you understand what I'm asking when you do that. Now let's go ahead and let's look at the next examples. The next examples are about radical equations. So we will have some radical equations to solve tomorrow. We're going to have some, we're going to start out probably, mostly they're going to be of the kind of simpler sort, more like number 6, but I want to show you one like number 7, so let's do both of those. For number 6, since the radical is already by itself isolated on the left side, we can then square both sides. So since it's by itself, you can immediately square both sides. If it would be a cubed root, cube both sides. If a fourth root, fourth both sides. So the square and the square root cancel each other out, leaving us 5x plus 7. Then we want to square 13, which is 169. We want to subtract 7 from both sides. And then you want to divide by 5. You should take a second to kind of check these, whether it's in your head or whatever. If you plug that back in, it does work. You get 162 plus 7 under the square root, which is 169. When you square the root that, you do get 13. So that's just a simple case. The ones we have to be more concerned about are ones like number 7. So let's do number 7. Now for a problem like number 7, that 1 is causing the issue. Take that 1 and move it to the other side, because we need the radical to be isolated completely by itself on one side of the equation. So if I subtract 1 from both sides, that's what I get. Now, we're going to proceed kind of like we did problem number 6. We're going to square both sides. Now here's where you have to be careful. It's easy to square the left side. The square and the square root are inverses. They cancel each other out, and it's just 2x minus 2. But the right side, please remember that you want to think about that as x minus 1 times x minus 1. So you do want to square that. So when you square it, please use your rules of distribution, FOIL it correctly. And so we get 2x minus 2 equals x squared minus 2x plus 1. Now that's a quadratic. We've been exploring more and more solving things like that. And the strategy you want to use most of the time is to get it equal to 0. So I like to keep my highest power positive. So let's keep that's where it's at on the right side. And let's move these things to the other side. So let's take the things that are on the left and let's move them over to the right so that we can get this equal to 0. So that's what we get. So we get a standard quadratic. Now, the strategy you want to use to solve this is what? Where do you want to go next? You want to unfoil it. You want to factor it, right? So you're going to take and you're going to ask yourself, how does that factor? And that one factors pretty good. The factors of 3 that are going to add up to 4 are the only factors pairs that make a 3, 3 and 1. So it's x minus 3 and minus 1 because the negatives are going to give you the negative 4, and a negative times a negative is a positive 3 that you see there on the end. And now you solve each one individually. So this is x minus 3 equals 0, x minus 1 equals 0. So x is 3 or x is 1. Now because we had x's on the inside of the radical and x's on the outside of the radical, you definitely want to take and check these back in the original problem. So let's just think about if 3 were to be plugged into the original problem. We get the square root of 4, because that would be 6 minus 2. So the square root of 4 plus 1 equals 3. Well, that's a true statement, so that one works. Now let's plug 1 back up into the original statement. We get the square root of 0 plus 1 equals 1. That's a true statement too. Always take and check these, because sometimes you get one thing that works and one thing that doesn't, or maybe both doesn't work. Because of the fact you're squaring something and you have x's inside and outside, it could cause issues. Always check it back in the original problem. So that's some radical equations that we might have tomorrow on the quiz. I would like to do number 9. Let's not worry about number 8. I'm not sure if I have enough time for that, so let's do number 9. So the first thing we're going to do for number 9 is we're going to isolate that radical. Let's take the 32 and let's add it to both sides so that we can get rid of that 32 is causing the issue. Okay, so that's what we get. Once we've isolated the radical, we can use powers to get rid of the radical. So this time we're going to use the 4th power. Now I'm not going to take the 4th power of 27. I'm going to hold it because I'm going to show you why in a second. So I'm just going to write 27 to the 4th just because I know what's coming. Okay. On the other side, this 4th radical and the 4th power are opposites. They cancel each other out. So we're just left with that. Now we have a power here. In the problems we've had so far, we have taken and gotten rid of a radical using a power. So to get rid of a power, we use a radical. So we are going to take the 3rd root of both sides. Now the 3rd root is nice. We don't have to worry about things that might not work, because remember, positives works, negatives work, everything works. The 3rd root and the 3rd power are going to cancel each other out. So that side is nice. Now let's talk about the right side, why I held it. You can do the 4th power first, or you can do the 3rd root first. Yeah, the 3rd root cancels the 27. What is the 3rd root of 27? It's 3. So that's why I kind of held it, because I knew that I didn't want to have to do that in my head. So the 3rd root of 27 is 3. So this is really just 3 to the 4th. Now I can do 3 to the 4th in my head, because that's just 9 times 9. So that's just 81. So that's 81 equals 6x plus 3. Now you're going to subtract 3 from both sides. So that is what? 78 equals 6x. And then we're going to divide both sides by 6. And we get that x is 13. Now, if you plug it back into the original, it's going to work. There's nothing that's going to screw up the cubed root. But we might get something that's, or the 3rd power, but we might get something that screws up that 4th root. So take a second and plug the stuff back in. If we plug 13 into this, we get 81 to the third power, fourth rooted. Well, you can take the fourth power of 81. It is positive. There's nothing that's going to screw it up. It does work. So that is problem 9. So now let's talk about some problems that are going to occur on the quiz about turning points and zeros and finding them. So let's start with number 10. It says state the number of possible real zeros and turning points of each, and then find all the zeros by factoring. So let's start with number 10. For problem number 10, the lead term is our highest power x squared. We know that the most number of possible zeros would be 2, turning points would be 1 less than that 1. So that's what we know about the function. We also know that it's going to look like a parabola that points upward. So now it says to find the zeros by factoring. So remember what you do. You take that function, you set it equal to 0, and you try to think of the ways that it can factor up. Well, we are looking for the numbers that multiply to give us 26, but have a difference of 11. So, start breaking down 26. So 26 and 1, 13 and 2. Hey, by cutting it in half, I already found what the two factors are. 13 and 2 have a difference of 11. So it's going to be x minus 13 and x plus 2. And then you're going to solve each individual one. We've done that enough that hopefully you recognize that this one will change sign to a positive 13. This one will change sign to a negative 2. So those are the zeros for that one. That's as far as you have to go. You're done. That's number 10. Let's take a look at 11. For number 11, the lead term is 3x to the 5th. It's going to look something like that if we really wanted to look at what the picture's going to be. That's the ends you're going to tell us. There are possibly 5 zeros and 4 turning points. That doesn't mean that I'll find all of those, but that is the maximum number I could find. We're going to take our function. We're going to set it equal to 0 to find the zeros. Now for this one, there is a greatest common factor in all of the terms. The greatest common factor can be numerical or a variable or both. So remove as much as you possibly can. And I can remove an x cubed from all 3 terms. Now when I remove an x cubed from all 3 terms, just the powers are going to go down by 3 on every term. So we get 3x squared plus 2x minus 1. Now this is a perfect case of slide and divide. I think it's just a perfect case of slide and divide. So let's take this and see if it factors down one more time by using slide and divide. So I'm going to take this 3 and I'm going to slide it over here. And I'm going to pretend that that was the problem they gave me. And I'm going to factor it. And so it's going to be x plus 3 and x minus 1. Now you slid over 3, so now you have to divide it back off. So we're going to divide that 3 back off. And then we'll get the true answer that we had. So it's going to be x plus 1. Now 1 doesn't divide by 3, so remember, to make it so that it's non-fractional, take that denominator and pop it onto the x as a coefficient. And so that's going to be 3x minus 1. So now we factored it. And if you have a different method, go for it. And now you're going to set each piece equal to 0. So x cubed will equal 0, x plus 1 is equal to 0, and 3x minus 1 could be the thing that was equal to 0. Now solve each one individually. This power goes away because we could just cube root both sides. So x is 0, negative 1, or this goes back to fractional. The 1 becomes the numerator, the 3 becomes the denominator again. So that is number 11. Let's go ahead and do number 12. If you find the lead term for number 12, it's x to the 4th. So we might have possible 4 zeros and 3 turning points. The graph looks something like a quadratic pointing upward. Now let's find the zeros by factoring. Now this one you'll notice has 3 terms. It kind of follows the quadratic model. Look at how the powers go. The powers go from 4 to 2 to nothing. So remember, if it goes a number, then half the number, then nothing, it's probably going to do one of these things. It's probably going to do one of those things. And this one does. It goes x squared here and x squared here. And we want the factors of negative 10 to subtract and give us 9. And so it would be positive 9 and negative 1. Now this is a sum of squares, and this is a difference of squares. Sum of squares do not factor. Oh, I'm sorry, that should be a 10. Sum of squares do not factor in the real number sense. They factor for with i's in them. So this piece we're going to ignore for now. It's not going to show up on our graph anyway. This piece can factor one more time. And so we get 2 zeros. We get a 0 when x equals negative 1 or positive 1. And if you want to write that as like the plus or minus 1, that's perfectly fine. The front factor didn't factor further. If this x squared had a minus 10, you would get a positive square root of 10 and a negative square root of 10. But since it has a plus there, it just doesn't factor. Okay? Let's go on to the next thing. This is just all about the lead term test and the end behavior. That is something that I will ask you about tomorrow on the quiz. So remember, you're just going to locate the lead term. So in 14, our highest power is a negative 7x to the 4th. And you're going to ask yourself, well, what would that graph look like if that was just my equation? Well, if the lead term is a negative 7x to the 4th, my graph will look like a parabola, something like a parabola that's upside down. So both of my ends are going to negative infinity. So that's enough reasoning to give me. Okay, you don't have to tell me anything more than that. But I would like you to write it in the correct notation. So let's practice writing it in the correct notation. The left end is the limit as x goes to negative infinity of our function. So our left end is what the left side is doing, and that's going to negative infinity. Remember, end behavior is your height. What height am I going to on the left end? That's left end behavior. Right end behavior is written like this. The limit as x goes to infinity of my function. And remember, that means what height am I going on the right end? And I'm going to positive infinity. Or, I'm sorry, still down, negative infinity. My x's are going to positive infinity. My function's height is going down, negative infinity. Let's look at 15. The highest power on 15 is a negative x to the 5th. That's our lead term. The negative on front will take the x to the 5th and flip it over. So it traditionally looks like a cubic. Now the cubic just gets flipped over. So it looks something like that. Now the other terms are going to make some bumps in the middle, but this is just asking about the ends, so that will tell you what the ends are doing. So let's think about our left end is going up, our right end is going down. So now let's write it in a formal way. The left end is the limit as x goes to negative infinity of our function. You can see from that that our left end is going to positive infinity. So that's your left end is going upward to a height of positive infinity. My right end is going downward and will reach a height eventually of negative infinity, if there is such a height, okay? So that's all I need for the end behavior with the lead terms. You can just draw me a little picture of what it kind of should look like, and then tell me what your end behavior happens to be. Okay. Last example. So if I ask you to find a polynomial equation with these real roots, we have done an example like this in our notes. Remember that the polynomial equation would be the function equals x minus the 0 times x minus the 0, however many of those you need for each 0. Now we're finally finding the simplest equation. There are multiple equations that have these roots. I just need the simplest one. And so it will be x minus 3, x minus 2, and x plus 2. So it's the opposite of what you're plugging in, because it's minus that particular number. Now when you do these, you may multiply them in any order. Because these two are opposites, they are going to multiply nicely. So I'm going to multiply those ones first. You can do it in any order. It's up to you, because multiplication is commutative. Feel free to mix it up however might work nicely for you. And so I'm going to do the back two first. Now x plus 2 times x minus 2 is the opposite, or the going backwards with our perfect square formula. So it will multiply and give us our perfect square. So this is going to end up being x squared minus 4. Now if you want to actually FOIL it out and check each term, you're going to get a plus 2x and a minus 2x that will cancel out in the center. So that's why I wanted to do those two first, because instead of getting 3 things, I'll get only 2. Now from there we can distribute. So we're going to distribute the x to both of those, and that's x cubed minus 4x. And then we're going to distribute the negative 3 to both of those, and that's negative 3x squared plus 12. And then if you could, please put your final polynomial in descending order. So highest power to lowest power, and that's going to be x cubed minus 3x squared minus 4x plus 12. So that's all the material that's on the test, or on the quiz. So you'll have all class time tomorrow to work on that quiz. And it will look similar to this with a mixture of equations. Please, I would look over the note cards, especially any of the ones that related to the questions we just did. Those are, that's the sheet that you would want to look at as well. Make sure that you remember what each thing kind of looks like. So I would take some time to just remind yourself what the parent power functions look like. and then you'll be prepared.